Hello, friends. Welcome to Science Talk. I'm your host and resident oceanographer, Jim Massa. In this video, I want to kind of bring together some of the major points I've been sharing with you in some of my recent videos. And namely, I want to bring together what's happening in the Arctic, kind of give you a summation of what's going on in the Arctic. I'm sure you all know exactly what's going on through my work and others. And at the same time, I also want to bring together, tie this into a recent video that I made where I talk about how stable oceans is not a good thing for the planet. So starting with the Arctic. So what do we see going on with the Arctic? We see that the Arctic is warming up very fast. We have it's warming up too. Now, a lot of the estimates are 3 times faster than the rest of the planet. We saw what happened earlier this year with the Siberian fires. Not the only fires in the Arctic region, but it was the one that was definitely caught the attention of folks. We know what's going on with the Arctic sea ice. I've shown you the graphics of that. The Laptev Sea, that area off the Eurasian side of the Arctic Ocean, is there is no sea ice there. The projections are that the Chukchi is on its way to becoming ice-free, as are the East Siberian, the Laptev, the Kara, and the Barents Sea. And we saw that. So, of course, when you have no sea ice, that's open water. Open water absorbs sun energy. No ice means no reflection of heat energy back into space, no cooling down of the region and of the planet. So now we have open water absorbing the heat energy. That absorbed heat energy is a reason why sea ice forms later and later in the year. Now, keep in mind, September is the oceanic summer. So that's when we expect to see sea ice at its minimum, just like March is the oceanic winter. So sea ice will be at its maximum in that period. This is for the Northern Hemisphere. But when you have such low extent, or when you have like no ice, in the past we said it would be the lowest extent, but there still would be ice. Now we're just having no ice in a lot of the region. That is absorbing so much heat energy. And so it's going to take longer to cool down because there's more energy to give off. And don't forget, seawater has to cool below 0 C to form sea ice because you have to have brine rejection. And so we're getting longer and longer it takes to freeze the sea ice. And in so doing, as the heat is giving off, it's given off to the atmosphere. That keeps the land mass, the air mass over the land, warmer for longer. Such that, as in Alaska, for example, October is the month that has warmed the most compared to the other months of the year for Alaska. And it's due to the fact there's no sea ice in the Arctic Ocean, so all that latent heat energy is given to the land, and we stay warmer. And we notice this, that especially over the North Slope, it's really much warmer than usual, and then the levels of being much warmer decreases as you get more and more towards Prince William Sound in the Gulf of Alaska region. So we have that. I discussed with you how not having the sea ice present, melting, freezing later in the year, melting early in the year, we're losing out on ice edge productivity. And so so now we have open water, but until the angle of the sun is high enough, the open water phytoplanktons can't get enough energy to activate the electron transport chain system that's found inside the chlorophyll to start the photosynthesis process. So sea ice productivity, or just primary productivity, is reduced. This has negative consequences for the food web in the Arctic Ocean. A warming air dries out the ground, making it more prone to fires. Another reason why we saw the big fires in Siberia. We know about the breaking 100 degrees Fahrenheit in Verkhoyansk, Siberia. That wasn't a one-off. If you look at the temperature data, it's just warming. See the same thing here in Alaska. Although this past year, because thanks to the situation of the Arctic dipole, we're a little cooler than usual, but recent data is indicating we're now on the slightly warmer than average side of things. Be that as it may. The Arctic is warming. So now with this warming, of course, you got the ground drying off. You got the permafrost thawing. That sets up a positive feedback loop. You've got, giving off methane into the atmosphere. Very potent greenhouse gas, causing more warming, causing more thawing, more release of methane. We're seeing the ground slumping. Right? We're seeing whole chunks of real estate falling, where settlements and villages have to be relocated. And now we have the issue of the methane time bomb. In other words, all the methane, in the forms of the hydrates, all rimming the shelf of the Arctic Ocean, the continental shelf. That's just leaking away methane. And thanks to the work of Natalia Shakova and her husband, Igor Smeletov, they're doing a lot of the groundbreaking work, finding out how much is there, what rate is being released. And Natalia's been working on the issue of the methane hydrates in the continental shelf ringing the Arctic Ocean. Igor has been looking at the permafrost in Siberia. And this is a major concern. How much is there and what rate will be released? Will it be released slowly, or will there be a big fart event, as now being called? So that's also a major concern. If that were to happen, that's not going to bode well. It's not going to bode well at all. So you have the issue of no sea ice, warming oceans, warming atmosphere, ground drying out, leading to more fires, more permafrost thawing. You got the methane hydrates in the continental shelf of the Arctic Ocean. That's being released. There's a lot of things coming together, and it's coming together fast. And we put all these factors together, and things are increasing exponentially. And basically all the positive feedback loops are kicking in, and this is not good. To be quite blunt about it, this is not good at all. So when you hear people saying, well, we haven't quite gotten to the tipping point, I'm going to beg to differ, and I am of the opinion, and my assessment is based on the data, based on the incoming data, that I think the tipping points have been blown past. I hate to say it, but that's my honest assessment. I don't want to be here, sound like all gloom and doom, but that's what the data is telling us. And to ignore the data would be silly. So now, how does this tie into what's going on with the ocean? In my recent video segment, I discussed how the stratification of the ocean is not a good thing. In fact, it's a terrible thing. And this ties into what's going on in the Arctic, because what happens in the Arctic does not stay in the Arctic. Right? If you're warming up the Arctic region, you're warming up Greenland, so Greenland is melting away and it's dumping all that fresh water, so that you start slowing down AMOC. Even eventually will shut that down, and it is slowing. We've got the measurement. AMOC, the vertical formation sinking, is slowing down, and since AMOC pulls the Gulf Stream along, the Gulf Stream is slowing down, right? Which means it's going to leave hotter water off the eastern seaboard of the U.S. Hotter water is thermally expands, so sea level rises will continue. But without having that vertical sinking does accomplishes several things. First of all, if you go back in terms of what humans are doing by adding the CO2 into the atmosphere, it's a way to sequester that CO2 from the atmosphere and the upper oceanic water layers, down to depth as the water sinks. It also sequesters heat. Right? So it brings the heat out of the upper layers down to depth. But it's vertical mixing. As I explained in my, I now call it the OMS video, in order to have productivity in any aquatic body, be it a lake or the oceans, you need several events. You need an overturn event, which means the water column overturns from top to bottom, and that therefore brings on mixing, and this is from the result of density currents. When you have water sinking vertically, that's a density current, because basically the water that's on top is more dense, so it will sink through the water column. That's vertically, right? And so you need this overturn and mixing, followed by stratification, where you stabilize the water column. But what that does is it locks the phytoplankton along with the nutrients into the photic zone. Now, you may, through wind action, whatever, you may have a little bit of mixing within the photic zone, which is fine, because the phytoplanktons and the nutrients are not moved out of the photic zone. The photic zone is how deep into the water column light energy penetrates, so that is sufficient for photosynthesis to occur. So if you have mixing within what in the lakes is called epilimnion, right, in the upper layers there, that's fine. The phytoplanktons can carry on and do their thing. And we need that in the ocean. In fact, usually in the temperate regions of the ocean, you have what we call seasonal pycnoclines, where you get the mixing, you get a stratification because sun energy warms the water up sufficiently so that you can stabilize the upper 100 or so meters, and the phytoplanktons can do their thing, and the zooplankton do their thing, so on and so forth. Then that breaks down, right, as the nutrients are used up, as we get moved into the autumn and winter time periods. When you get into the tropical waters, because it's just so warm all the time, you pretty much have almost a permanent thermocline in the upper layers, so that you really don't have a lot of productivity in that region of the oceans. And then, of course, when you get to the polar region, it's more of a halocline, because the temperatures of the water is so cold, but it's, from meltwater, what have you, that the salinity is always changing. And that's what forms AMOC, as you guys know by now. Warm, salty water from the Gulf Stream gives off its heat, becomes cold, salty water. Cold, salty water is very dense, it sinks. Throw in a pile of meltwater from Greenland, it's not so salty anymore, it's not so dense, it's not going to sink. So we got that going on. So, but it's important because you take that CO2 and the heat and you bring it down to depth. But now, what happened? And keep in mind, right? We're taking the carbon dioxide that humans are putting in the atmosphere, bring it down to depth. What happens now as we continue to warm the planet, we continue to dump CO2, right? What's going to happen? Well, we're already seeing how sea surface temperatures are increasing. We're starting to stratify the oceans. If you start stratifying the oceans, we're not going to have that vertical sinking. You're not going to get that mixing. You're not going to get that overturn. That's not good. And here's another problem. Now, and think of this as added information to that OMS video I did. I did not discuss it at the time, but I figured it's a good place to bring up this point here. And I've done other video segments discussing this, so you can look at those. But we know that CO2 plus water equals carbonic acid. Okay? We know that the acidity of the ocean is increasing, the pH is decreasing. We know that. When you take the CO2 from the surface waters and sequester it to depth, you are helping to increase the alkalinity of the water, i.e. reduce the acidity, helping to do that. And then, but you're bringing that to lower depth. So what happens is, as you go deeper in the water column, you'll find that the pH will also decrease as well. So that the further down in the water column you go, you have increased acidity, decreasing pH. And it gets to the point that, and you factor in also pressure, what have you, but as you increase the pH of a solvent, you are able to dissolve more of the solute into the solvent. Eventually, you get to a layer called the CCD, which is the calcite compensation depth. Calcite compensation depth is the depth that below the CCD, calcite, which is the main form of calcium carbonate, you also have aragonite, but let's just restrict ourselves to calcite, remains in solution. Increased pressure helps keep it in solution, just like at the, when you go to the hydrothermal vent, the water coming out is at 400 C or so, and it's liquid because of the immense pressure down there. It's not a gas. But so you got the pressure there, but also because of the decreased pH, calcite stays in solution. Above the CCD, the pH and the pressure is such that calcite can precipitate. And where we see that transition from precipitating to staying in solution over through the CCD, we call that the lysocline. Organisms that are above the lysocline, they can precipitate calcite. They can make their shells. And if you're a phytoplankton, you can make your test. Test is just very thin. We are now finding, because the oceans are stratifying, we're not moving the CO2 out of the upper layers. It's kind of staying in the upper water layers. So in other words, we're really increasing the acidity of the upper water layers. By really increasing the acidity of the upper water layer, we are also now measuring that the CCD/lysocline is getting shallower and shallower, meaning that this is now affecting organisms' abilities to make their shells, their tests. They can't make their shells or tests, they will die. And we're starting to see that. Lysocline is getting very shallow. It used to be, depending where you are in the ocean, but it could be anywhere from like about 300 to 500 meters down. In some cases, now I'm hearing that the lysocline is as shallow as 80 meters, which is very troubling. And it's getting, and the data is indicating that it's getting shallower and shallower. So that is another major issue. Along with the stratifying of the ocean, not having a vertical mixing, okay, and you have warming water temperatures. Warming water temperatures also does what? It decreases the solubility of gases. So the ability of the oceans to continually absorb the CO2 from the atmosphere, the CO2 we're putting into the atmosphere, is going to decrease. At some point, you're going to reach solubility max. You're going to reach the maximum solubility for the gases, and the CO2 will then start to outgas back into the atmosphere. You start dumping more CO2 back into the atmosphere. We know how CO2 and temperature track. More CO2 in the atmosphere, more atmospheric warming. But also oxygen. Organisms that have gills need dissolved oxygen. A warming ocean means less dissolved oxygen. Those organisms are going to start to suffocate. I mean, if you're a cetacean, a mammal, what have you, break the surface, take a breath of air, go back down. Hold on to that thought for a moment. So you have those organisms and affected, but you got the warming ocean. Okay? If an organism prefers a temperature range of, say, 8C, but it's now finding itself in waters at 10C, that's too warm for it. It's going to start moving. And I've done videos where the organisms are moving to the poles to try and find cooler waters that's better suited for their physiology. If you're like a turtle, okay, you're cold, so you sit on a log or a rock and you bask in the sun, you warm up, and then you overheat, you take a dip in the water, okay, cool down a bit, climb back out. If you're an aquatic organism, where are you going to go? You're surrounded by temperatures that are too hot for you. So you start moving, start migrating. Then again, then you find an area that, okay, this is more suitable temperature, but where's my food? You're going to start seeing that kind of stuff. So you're having stratifying oceans. Stratifying oceans, you're not getting a mixing. Eventually, all the nutrients are going to be used up. What are the phytoplankton going to do? They don't have the nutrients. They may be getting the sunlight energy, but they don't have the nutrients to carry out primary productivity, photosynthesis, etc. They're going to start dying off. And phytoplankton provide 55 to 80% of atmospheric oxygen. You don't have to be a rocket scientist to understand that phytoplankton start dying off, oxygen content in the atmosphere will decrease rapidly. And guess what? We are already measuring a decrease in atmospheric oxygen. It's already taken place. So the oceans are suffocating. The oceans are dying. I'm just going to be very blunt about it. Yes, I'm an oceanographer, but this is the planet is Oceanus, not Earth. It's Oceanus, and what I see is very alarming, very, very frightening. To be quite blunt. We're almost on if we continue down this path, the planet's probably going to see another Permian type extinction event where 95% of all species goes belly up. Very serious shit going on here. And we know that, looking at the sediment and the ice cores, we can tell when the thermohaline circulation was flowing and when it was not. We know that, and we see the changes in the when you look at the diatomaceous oozes and you look at the forams and the radiolarian, we can tell when there was diversity in the water column, when there was not. And usually when there was diversity, the thermohaline circulation is flowing. When there was not, when it drops off, it's off. We see that. So we're in danger of having the ocean having layers with its anoxic, hypoxic, and we get this very stratified upper layers. It's not good. Not good at all. You're gonna see collapses of food chains. You're gonna see increased acidity, decreased pH, decreased gas solubility, and just warmer situations. And don't forget, one of the things when AMOC starts forming, and you get the conveyor belt, part of that branch surfaces in the Antarctic divergence zone. It's what runs that ecosystem down there. Why you have so much productivity of krill, which then feeds all the baleen whales and the seals and the birds and the orcas and so on. That can all collapse if the conveyor belt shuts down, and it is slowing. So, kind of trying to wrap this up for you guys here. The Arctic is warming. It's leading to warmer temperatures, air temperatures, sea temperatures, no ice, no sea ice, increased thawing of the permafrost, more methane in the atmosphere, drying out of the ground, more likely fires. And that's true anywhere, basically. Look at going on in the western U.S., California, Oregon, and so on. Right? Then you have the hydrates and clathrates on the continental shelf around the Arctic Ocean basin. That's releasing more and more methane. We've got Greenland melting. We've got the Thwaites ready to collapse totally. Pine Island right behind it. So we've got all this meltwater that's going to raise the sea levels, and by putting all that fresh water in there, you're going to further help stratify the oceans. You got all that going on. You got the slowdown of AMOC. Right? You have increased stratification of the ocean that's going to decrease productivity, lead to mass extinction, and will eventually cause an outgassing of CO2 back into the atmosphere, which will further accelerate the warming. And as you also increase this sea level rise along with thermal expansion, you're going to start drowning more and more coastline. A lot of that sea level rise will go up any major river drainage basin will go up that. So you're going to have these incursions of waterways into the middle of continents. For example, the North American continent was almost split in two by an inland ocean during the Jurassic. The Cretaceous started drying up a bit, and you had formation of the Rockies and other things going on. Sea levels started to cool down, so sea levels started to drop. But you can go to Colorado, New Mexico, and you can find places where, oh look, there is a fossil of a marine organism. Right? So that is also going to happen. Of course, with this, you're losing more and more land. You're going to create a lot of climate refugees. And where are people going to go? You now have all these people on less available land. Right? We're basically going to be causing our own extinction. I hate to say that. So things are not looking good. Things are very dire, in my opinion, based on understanding what the past has told us, the data, and just looking at the current trends. Because, as you've heard me say in my videos, if you want to know what's going on now, what was likely to happen in the future, look at the past. Right? And you take all these signs, all these positive feedback loops that are rapidly kicking in, such that things are accelerating exponentially, not linearly. It's becoming a runaway system. And this runaway system is going to create a lot of changes for the planet, and changes are not going to be good. So, kind of wanted to bring you this kind of a summary of the main points of the videos I have done in recent times, kind of try and pull it together. Of course, I'll keep you guys up to date on this stuff. But there you have it. The thing, in my opinion, the things to look for is what's happening with the oceans. I'm not saying that because I'm an oceanographer, but that's just, what happens in the ocean drives the rest of the planet. So, my concerns are the decreased productivity in the ocean. And don't forget, if you have decreased productivity in the oceans, that's less fish for the people who depend on the ocean for food. And nearly 3 billion people do. If fish start dying off, people are going to starve. If you start having salt water moving into areas that grow crops that require fresh water, crops are going to die. Less plant, people are going to starve. Right? This is what's coming down the pipe. This is where it's leading to. So, there you have it. Warming ocean, warming Arctic, thawing out Arctic, land drying out, conveyor belts are slowing down, deep water formations slowing down, ocean stratifying, increased glacial land ice melt. And don't forget, hotter temperatures means reduced plant yields, reduced nutritional quality of the plants, and then you start throwing saltwater incursions in there, all stacking up to be not a very good situation. So, yeah, if you haven't seen my videos on overturn mixing stratification or why stable oceans are bad, please check those out and so forth. So, there you have it. Thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.